All right, so as a quick recap, we have gone through a ton of different tests. The last ones that we just got done doing were the comparison and limit comparison tests. And the ratio and root tests kind of look like those, right? We did the limit of a sub n over b sub n for the comparison tests. And for the ratio and root test, we're going to be doing the limit of a sub n plus 1 over a sub n. Notice there's also an absolute value there, and that makes things nice because if we have things like an alternating series, we can still use the ratio and root tests. So let's just go through the criteria here real quick and then go ahead and try one. So if we see a series that we think we can use the ratio test on, and as a hint for that, you're looking for typically n factorial. Any kind of factorial is a clue that the ratio test is probably a good choice. Another one is literally just a lot of n's. You know, if you got n plus 1 squared times 3 to the n over n minus 2 factorial, whatever, right? If you have a ton of those, a ton of n's running around, it's a good choice typically to try the ratio test. So we're going to take the limit, and the a sub n plus 1 just means anywhere you see n, turn it into n plus 1. So we take that term, divide it by the a sub n, and we get some value out of it. We call that value L. And depending on what that value is, will tell us what the series does. If L is less than 1, it will converge. If L is greater than 1, it will diverge. And if L is equal to 1, we can't say anything. We have to try something else. The best we can do is say inconclusive. All right, so let me go ahead and try this first one here. So this is for a sub n plus 1. I'm going to do -3 to the n plus 1 over n plus 1 all in the factorial. Okay, so we want the limit as n approaches infinity. We want to start with this term. And again, instead of actually dividing by a sub n, which is right here, I'm going to multiply by the reciprocal, or 1 over, right, a sub n. So that's going to be n factorial, or -3 to the n. So now I want to start simplifying the best I can. So I'm going to expand the -3 to the n plus 1 as -3 to the n times -3 to the first. And then we've got times n factorial. Now n plus 1 can be reduced. Remember that if we bring that out of the factorial and then subtract 1 from it, that is the new factorial. Everybody remember we went over that?
Can you explain that one more time? I'm sorry, I missed it. For the bottom part, how you took the n+1 out?
So if I have, say, 5 factorial, I can start at 5 and multiply by every number below it until I get to 1.
Oh, yeah. Okay, never mind. I understand now.
Let's do it anyway, because I'm sure you're not the only one. So if I want to do n+1, you just start with n+1. The next one is n+1 minus 1. And you could keep going, or I can just stop at any point and call it a factorial. So that's n+1 times n factorial. All right, so then we look and see what can we cancel. So I've got -3 to the n, -3 to the n factorial, n factorial. So I now have the limit as n approaches infinity. Absolute value of -3 over n+1. So the absolute value I can drop if I just turn the -3 into +3. And the reason that that doesn't affect n, or I don't have to worry about it, is if n starts at 1 and then goes to infinity, it's always positive. And therefore n+1 is always positive. So I just need to evaluate this limit. It's pretty easy. It's going to be 3 over infinity and 3 over really big numbers. Looks like 0. That is less than 1. So if we go back to our rules, if L is less than 1, the original series converges. So let's say, therefore, A sub n converges by ratio test. Everybody go with that one? So I think I might do C here and let you guys do B and D. So this is all A sub n, right? Okay, so I want to do the limit n approaches infinity, absolute value. Now, anywhere I see n here, I need to make n+1. So I need n+1 pi there. Then I need the third root of, now because it's already n+1, I'm going to make this n+2. N squared is now going to be n+1 squared. And that'll be 3 to the n+1. Everybody okay with that?
No, 4. So you have cosine n+1 pi, but the cosine, the original function, is n times pi. And but if you were to put in like the thing on the right, it would be cosine n plus pi instead of multiply. Wouldn't that be the case?
No, this would be cosine of n pi plus pi. You'd have to distribute the pi.
Oh, that's true. Okay. So
I think maybe you're thinking ahead.
I might be. I'll let you do your thing.
Hold on a second. Let's see if it makes sense. So that's the every term with n plus 1. We then need to multiply by the reciprocal. So we need n squared times 3 to the n all over cosine n pi cubed root n plus 1. Then close up the absolute value. All right, now we got to try and cancel some stuff. So what can we cancel here? Well, let's go ahead and rewrite the whole thing. Separating out anything that we can. So it really looks like the only thing I could break apart was this 3 to the n plus 1. So I'm going to cancel the 3 to the n's. Now, at this point, n squared, n plus 1 squared, cubed root of n plus 2, and the cubed root of n plus 1. All of those quantities are positive because n's 1 to infinity. You're adding numbers to it, you're squaring them, and so forth. So none of those could be negative. This 3 down here, positive already. Excuse me. What about the cosine n pi and the cosine, n plus 1 pi? What do you think happens to those?
Are they alternating?
So cosine n pi is alternating, and so is n plus 1 pi. So any alternating term, when you take the absolute value, becomes what?
Doesn't it just get rid of it?
So it becomes 1, basically. So we have limit, n goes to infinity. I'm going to drop the absolute value, which means this and this are going to go away. And then I'm just going to write the cubed roots together. There's still a 1/3. And write the squared terms together. Guys, still with me? Give me one of the, yeah, a little virtual thumbs up's fine. Okay. So what I'd like to do now is put these cube roots together and these squares together, and then evaluate the limits. So this is going to be the cubed root of n plus 2 over n plus 1. Again, there's still a 1/3. I'm going to go ahead and throw it out in front. And then n over n plus 1, all squared. In each one of these, I'm going to divide everything by n, right? The highest power of n in the denominator is n to the first. So I'm going to divide every single term by n. Okay. So now, if I were to evaluate the limit of, say, the cubed root here, the 2 over n would go to 0, and so would the 1 over n, right? You have two terms that you're dividing by infinity. So this little guy would go to 0, and so would this one. That would leave you with the cubed root of 1. And this piece over here, if I do the 1 over n, it'll go to 0. And you'll be left with 1 squared. So this whole thing just comes out to 1/3. Again, that's less than 1. And if we go back to the rules really quick, less than 1 converges. So we can say, therefore, converges by ratio test. Okay. So any questions about that problem? All right. So let's go ahead and look at the root test. And after I do two, or I guess I'll do an example, maybe two, we'll see. I'll let you guys try this in your groups. Let me see which one of these I want to do. I typically give you guys C here, but let's see. So I'm going to go ahead and, all right, so this time, instead of a sub n plus 1 over a sub n, we're only testing a sub n. Excuse me. So then you're doing the nth root of the absolute value of a sub n. And then the same rules apply. You get an L. If that L is less than 1, converge, greater than 1, diverge, equal to 1, inconclusive. So I just want to jump right in here and take the limit as n approaches infinity. of the nth root of the absolute value, 7n plus 5n squared, 6n squared minus 5. This is all to the nth power. So first thing I need to do is the whole reason of using the root test, right? Just like the ratio is good for things that had factorials, the root test you should use for series that have everything to the power n. They don't have to be, right? Not every single term has to be to the power n, but this is most useful when everything is power n. All right, so the reason for using it, as I said, is to get rid of that power n out there, but we can't do that until we get rid of these absolutes. So the question is there any way for this stuff inside the absolute to be negative? Well, n runs from 1 to infinity, so n is always positive. So 7 times a positive number plus 5 times a positive number squared. There's no way for that to be negative. What about the denominator? There is a minus sign down there. Well, if n starts at 1, you get 6 minus 5, which is 1. And then every subsequent value is going to be greater than 1. So that is also always positive. So if you have positive number divided by positive number, all to the nth power, also positive, then the whole thing is positive all the time. So I can get rid of that absolute value right off the bat, just from that argument. And now I have the nth root of all this stuff. And that allows me to go ahead and get rid of the root and the power. Now I just need to evaluate an infinite limit, which again, I divide by the highest power of n in the denominator, which is n squared. So divide every single term by n squared. It'll cancel completely there, and one of them there. And then when applying the limit, anything that's divided by n to a power, a positive power, will head towards 0. So we get 5/6. That's less than 1. Therefore, a sub n converges by root test. Okay. So I don't think the concept here is difficult by any means. I think it's just very algebra intensive. So if you're not good with your exponent rules, or sometimes factoring, or factorials, those sorts of things, this can be troublesome. Or I guess maybe evaluating limits as well. Let me just rewrite this last one here. I think I'm going to go ahead and let you guys try these. So I just want this to be clear that this is n times, this is 4 to the n over 3. So do you all feel comfortable to go ahead and try these? So it'd be both root test problems and the ratio tests that I left behind. Anything that resembles a yes or no would be greatly appreciated. Hey, a thumbs up. 2 thumbs up. Oh, here we go. Take that, Roger and Ebert.
I'm confused on problem C for the root test.
Okay. So I'll run through it real quick. Can you guys see my paper?
Yeah.
So I would rewrite this as four to the 1/3 over 7, all to the n. You okay with that?
Yeah.
All right. So then we go ahead and take our limit and approaches infinity, nth root, absolute value. Really, we don't need the absolute value because everything there is positive, so we can drop it. Then nth root, we'll cancel with that n, but then it still will be on this n. So this 4 to the 1/3 over 7 just comes out. And then we have n to the nth root, or 1 over n. Okay with that?
Yeah.
All right. I'm going to throw this number out in front. And actually, I'm just going to say, because I don't feel like writing it, let a equal that. Okay, just some constant. So this is now a limit n approaches infinity, n to the 1 over n. I am now going to call this piece y. So then I'm going to take the natural log of y and set that equal to limit n approaches infinity of the natural log. Ooh, natural log n of 1 over n. Now the question is, why in the world did I do that? Well, if you try to evaluate the limit back at this step, you get infinity to the 0. That should tell you you should be using L'Hopital's rule. And if you have a power that is one of the variables, then a natural log is the only way to get it down. And we also know to use L'Hopital's rule, we need a ratio or a fraction. So the log allows me to bring that 1 over n down. So I'm either multiplying by 1 over n or dividing by n. Same concept. Now if I try to plug in, I get infinity over infinity, which says now you may go ahead and actually use L'Hopital's rule. So this is going to be 1 over n all over 1, right?
Right.
My limit here. However, the limit of 1 over n as n approaches infinity is 0. Right? Because you have 1 divided by really big numbers. But again, this equal to that. E of both of them, then I get that y is equal to 1.
Okay.
So now it looks like left over I have a times 1, right?
Right.
So now when I'm doing this, I realize looks like whether you include this or don't include this makes it different. Unless I just did something silly. Give me a second here. So I don't think that I can leave the the a out. And therefore, if I leave it in, it just comes along for the ride. It's just a multiplier. And at the end, a times this limit goes to 0. You still get e to the 0. And you just get 1 at the end for the whole thing, which is this. But I will double check that.
Thank you.
Did I confuse you or are you okay?
No, I'm okay now.
All right. Because now even I'm questioning why I can't take that a out of there. I should be able to call whatever I want y and it should still work out. So I'm gonna have to do that one again. But for now, we're gonna go with this. All right, so the last little bit of time we have left, I would like to do at least one of these power series interval of convergence problems. First, I have to give you a little introduction to power series, and then I'll go ahead and try this. So first off, what is a power series? So a power series is basically changing any kind of function, typically something we would call a transcendental, like a trig function, exponential, logarithmic, something like that, into a polynomial. Right, we know from experience that derivatives, integrals, just graphing, multiplying, whatever, we have a ton of rules and we should be pretty good with polynomials, right? They're much easier to work with than, say, sines and cosines. Right, we have an idea of what x cubed minus x squared looks like, but we have no clue off the top of our head what sine cubed minus sine squared might look like. So power series allow us to take those functions and turn them into polynomials. So there's a little example here. It just says here's a basic exponential, e to the x. And eventually we will learn how to get to this form here. And they use this form and write out the first couple terms. So here's the first 5 terms of the power series expansion of e to the x. And this is the nice closed form of the power series. And then there's another little tidbit here. It says that power series, any power series can be written in this form. So it's some coefficient, some number, c sub n, times x to a power. So all this is great, right? That's the purpose for a power series. We want to basically take integrals and things like that we don't know how to solve or are difficult to solve because of them having trig functions of exponentials and logs, and use an approximation, so a couple terms of the polynomial or power series, and that will allow us to then solve problems in a easier way. But as all these series before, right, they're no good to us if they don't converge. So notice at the first bullet point here, it says the power series is convergent if x falls between -1 and 1. Another way to write that is absolute value of x less than 1. So notice, if that's for converge, where else have we seen something less than 1 gives us convergence?
P series.
I think you're thinking of the geometric, right?
Yeah.
And then more recently, we just did ratio and root. So both of those said if the value that you get is less than 1, it converges, right? So we're going to use one of those two in order to help us find the interval of convergence. So I'm going to skip A because A is a strange one to start with. I am going to go ahead and do I guess I'll do C here for you. So very first thing that I want to do is start with either the ratio or root test. This one you might start with the root, but recall we just got done doing that problem where we had to take the natural log and all those things. That would occur here as well because this n right here is not to the power n. So I'm going to start with the ratio test. That says take the limit as n approaches infinity, absolute value. Anywhere I see an n, I'm going to make it n plus 1. Then I'm going to multiply by the reciprocal of what I started with. And the whole point of this is to make sure that this converges. So I have to say that this has to be less than 1. Right? By the ratio test, this whole thing has to be less than 1 in order for convergence. All right, so let's start breaking this up. Is everybody with me still? Okay. So I've got 2 to the n, 2 to the n. I've got 4x plus 3 to the n, and that again. Now I'm going to group the n terms together, and then everything else together. So I've got limit n approaches infinity, n over n plus 1. And then I've got 4x plus 3 all over 2. Still all must be less than 1. All right, now, as always, n starts at 1 here and goes to infinity. Therefore, this n over n plus 1 cannot be negative. However, there is a chance for x to be negative. So I'm going to do 2 things here. I am going to pull the 4x plus 3 over 2 out in front of the limit because it is not dependent on n. I am also going to leave the absolute value around it because there is the possibility that it could be negative. Are we all okay with that? I need to evaluate the limit. Divide everything by n. So the limit is going to be now 1 over 1 plus 1 over n. All of that is 1. Again, still all must be less than 1. So we are currently at this. So that inequality there, because the absolute value says that number has to fall between -1 and 1. Now recall that to solve an inequality, we have to, if we do an operation to one part, we have to do it to all of the parts. So I'm going to multiply each one of these by 2. Then I'm going to subtract 3 from all of them. And then finally divide everything by 4. So we have this. I would love to say that we were done, but unfortunately we are not. So this is our interval, but our task now is to determine, can x be one of those two endpoints? Can it be equal to -5/4 or can it be equal to -1/4? So far the steps are: start with the ratio or root test. Make sure it's less than 1 to converge. And then once we get to our interval, we are now going to test the left endpoint and the right endpoint. So when I say left endpoint, I mean let x equal -5/4. The original summation was 4 times x plus 3 to the nth power all over n times 2 to the n. And instead of x, I am plugging in -5/4. So now we need to see, what does this look like? Okay, well, we've got 4 over 4. Those would cancel. -5 plus 3, that's -2 to the n over n times 2 to the n. I can rewrite that as that guy, right? Because the -2 and the 2 are both to the power n, which means I can put them together, all to power n. And now I have -1 to the n over n. So I would like you guys to please answer me for this one. Are we okay so far? Because this is usually when students go off the rails at this point here.
I'm good.
Okay. Anybody else want to chime in? All right. I can only see a couple of you, can't see all of you. Okay. So a good bit of you said you're good, so I'm going to go ahead and continue. Now, the reason I say people like to go off the rails here is they think all the time you just take the limit as n goes to infinity. That's going to be a lot of the time, but not the only thing that you do here. So we took the left endpoint, we plugged it into the original, and we have a new series. So now you need to ask yourself, what kind of series is this?
Alternating.
So if this is an alternating series, how do I test it? And I'm not just saying alternating series test, that's obvious. What are the
Take the absolute values.
So I need to prove that it's decreasing, right?
Yeah.
And to do that, I need the absolute value of h of n. Which is 1 over n. 1 over n looks something like that. So that is enough to say that this is decreasing. The second part for an alternating series says take the limit as n approaches infinity of the absolute value of a sub n. That's going to very easily give us 0, and that meets the second criteria. So this series converges. If it converges, that means x is allowed to be that value. And I can be equal to. Then I go to my right endpoint, which is x equals -1/4. And I plug it into the original problem. Again, the 4's cancel. This time I get -1 plus 3 up top. And that's going to give me 2 to the n over n times 2 to the n. That's really nice because these 2 to the n's will just cancel completely. And I am left with this guy. Does anyone recognize that series?
P series.
It is. It's a very special one. Do you know what it's called?
Is it the harmonic one?
Yep, it's the harmonic series. And remember, I told you if you see a harmonic series, all you have to do is say harmonic, therefore diverges. So if it diverges, that means it is not equal to. So the very last thing you should do is write it in interval notation. Okay. So that is the interval of convergence. And all that means is if the value of x is anywhere between -5/4, including 5/4 or -5/4, up to -1/4, then that series will converge. So if you think about it, this is kind of a powerful tool in that before we had to test every single series that we saw. But at this point, we've taken a series that has an x in here, which is something we could replace with a bunch of different numbers. And now we've proven that this series, as long as x falls between those two numbers, will definitely converge. So again, we started with the ratio test. We simplified. We got our inequality. Solve the inequality. Once we have those endpoints, plug them back into the original. Look at the series that you get out of that and determine how to test it. So the one on the left here was an alternating, so we used alternating series test. The one on the right was the harmonic. The left converged, the right diverged. Therefore, we included the left point and excluded the right point. So there's a lot to this, a lot of steps. It's very tedious, but effectively no calculus, right? minus the limit, I guess. So would you guys feel comfortable doing B? Stop sharing so I can see some of you. If you put thumbs up and whatnot. All right, let me just put it this way. It'll be much quicker. Is there anyone that does not feel that they're ready to go ahead and try one on their own? Does the clapping mean that you're answering yes to that question?
Yes. It's the best thing we have since, I mean, there is the raised hand, but it doesn't give you like a little emote. So,
Well, I mean, I can do the other problem, but it's a special case, and so it doesn't help a ton. I mean, at least I can at least set it up. So let me do that.
well, what do you mean by special case?
Just let me do it.
Okay, sure.
So I'm gonna do this first one up here. Again, I'm gonna use the ratio test to start. So I need limit, n approaches infinity, absolute value, x to the n plus 1, and then you add 1 in there. And because this isn't a fraction, I'm going to go ahead and divide by the original as opposed to multiplying by a reciprocal. And I need that all to be less than 1. So the x to the n cancels. This is going to be x. This is going to be n factorial. And n minus 1 factorial currently. So I would turn this into n times n minus 1 factorial to cancel that one. And I am left with, so I have x times n, right? So the x has nothing to do with n, but could be negative. So I can bring it in front and requires the absolute value. And I have limit of n. Now, if I evaluate the limit first, that limit is going to be infinity all day long, right? Which means I don't care what x is. But what if I plug in x first? What value of x would make this quantity be less than 1? So let me put it this way. If x equals 5, 5 times infinity is going to be infinity, right? If x equals -1, we get back infinity after we evaluate the limit. What value for x would make it so that if I then go to evaluate the limit, the number will be less than 1?
Like 0?
Oh,
0 is the only option. So that's why I said this one's really weird. It's that.
does that not like it? So does that say that the interval of convergence is from 0 to? What does that exactly mean in context?
It's saying that the only value of x that works is 0.
Okay.
And the other weird thing is I don't believe that they write it in, like, if you look it up in a text, I don't think they write it this way, which bothers me because it
Yeah.
can be 0. But again, I can look that up again.
Thank you.
But yeah, that's why I said this one, like, you follow the same rules, but then there's no endpoints to test because the limit screws it up. So it's good because, that's a situation you could run into. So it's good to see, but it's not exactly the best practice in terms of doing the whole problem. So I'm going to go ahead and put you guys in your rooms. I want you to try B for today. When you're done with that, you can take off if you like. I'll probably stick around till about 11:05 or so. Of course, if you guys still have questions, I'll answer them the best I can. Feel free to ask me questions about your test. I still have quiz 17 and 18 to get or to grade, and I will be sending out a quiz or two for you to do today. So any questions for me before I split you guys up? All right, so looks like do a new group. Oh, wait. Oop, that'll work.